So Archimedes property says that the natural numbers don't admit an upper bound. And we kind of sketched an argument by contradiction last time. We said, well, imagine they did have an upper bound. Then by completeness, they would have a supremum. But then s minus 1 wouldn't be an upper bound. So there's a natural number bigger than s minus 1. But then whatever that natural number is plus 1 is going to be bad. So let's write down those ideas. So let's suppose, for the sake of contradiction, that the set of natural numbers is bounded. Then by completeness, the natural numbers has a supremum. Call it s. That s is a real number. Okay, so I said s minus 1 isn't an upper bound. Why isn't s minus 1 an upper bound? Yeah.
Because the supremum is the least upper bound?
Yeah.
Take one off of that, it can't be an upper bound anymore?
S minus 1 is less than s. S is the least upper bound. So s minus 1 is not an upper bound. So since s minus 1 is not an upper bound, so let's go to the board and just go slow and just check some logical calculus. So, not s minus 1 is an upper bound on n. And let's just expand out what that means. If you happen to be one of those people who are an advocate for that as a symbol for not, fine. But I like being able to read my symbols. Okay, cool. So that means not. And then let's put the definition of an upper bound. So it is not true that for every n in the set big n is less than or equal to s minus 1. So not a universal statement is true, so there must be a counterexample to it. So that means there exists an n in the set big N such that little n is bigger than s minus 1. Nice. And that's something that occasionally is helpful to do in scratch work, but often isn't necessary in the final proof. So now that we have that, not being an upper bound buys us that. Since s minus 1 is not an upper bound, there exists some n in n such that n is bigger than s minus 1. I guess when we talked about ordered fields, we proved that you can add a number to both sides of an inequality, and there's actually like a theorem that you would want to label as the place where we proved that. But I'm not going to cite any of those because that would make everything much too long. It follows that n plus 1 is bigger than s. Alright, so like there's not many laws left, but why is this going to be a contradiction? Yeah.
We've already passed, or we're already greater than our supremum.
Yeah. So we found a thing that's bigger than the supremum, and the thing is in the set still. The supremum is supposed to be the supremum. There you go. That does it. Is n plus 1 a natural number? Well, let's explain why. So let's see, since n is in n, definition 2.5.1 implies n plus 1 is in n. But now we have s not being an upper bound on the set of natural numbers, because we found a natural number bigger than s. But s was by assumption the supremum, which has to be an upper bound. So there you go. How did that proof feel? That seemed like a pretty okay proof? Right, the clever idea is to think in terms of contradiction, then you just got to follow your nose. Like, here's a thing I know, here's what happens when I translate that, here's what happens when I translate that. Oh, look, I have a contradiction. And that is the idea of the proof. Yeah?
Is there a certain way to say the not in parentheses? Is it like an invert statement or a convert statement?
A negation is maybe a good thing to say.
A negation, okay.
Right, you're taking a statement and saying not that.
Okay.
I think the negation of the statement is the right thing to call it.
That makes sense.
Groovy. Cool. So let's sketch. Let's list the other things that could be called Archimedes property. So let's think about the set of integers. So it's a set of natural numbers, the set of negative whole numbers and zero altogether. The claim is that is neither bounded above nor is it bounded below. That sound believable? Yeah. Right. Well, don't worry about the proof. Like, yeah, that's something that you certainly believe. We will prove it. The other things that might be called the Archimedes property is if you take any positive, if you A and B are real numbers, and A happens to be positive, then you can multiply A by a natural number to get it to be bigger than B. So if I start with a really, really, really small but positive real number, and then some other really big real number, I can multiply the little one by a big enough natural number to get it bigger than the big one. Yeah. Like 1 billion times 0.01 is probably bigger than a fifth. There you go. That's what this second theorem is saying. Archimedes property version 3 says that if you take the infimum of the set of all reciprocals of natural numbers, that infimum is 0. Does that seem believable? Yeah, right? Like, 0 is certainly less than all of them, but the infimum can't be anything bigger than 0, because 1 over n should get real small. And the final goal is this, the density of the rational numbers. For any real numbers, x and y, with x less than y, you can find a rational number between them. And that's another thing that I hope you believe. So hitting those results are our goals today. Let's try to do them. Yeah, it's just x and y with a q between them. For every x and every y, you can find a q between x and y. That's informally what that theorem is saying. We'll get to it today. So, let's go through one at a time. So, corollary 2.5.4, the set of integers is neither bounded above nor bounded below. So this is labeled as a corollary. And that should mean that the proof should be like pretty easy if you assume the thing that we just proved before. So let's assume that the set of natural numbers is not bounded below, and then try to prove the corollary. And let's proceed by contradiction. Let's suppose that z is bounded above. Let's let u be an upper bound for z. If u is an upper bound for z, does it follow that u is an upper bound for n? Yeah, let's try to explain why. So if you want to show it's an upper bound, then I guess you need to consider anything in n and convince yourself that this thing is bigger or equal to that n. So let's try to do that. Explain why u is an upper bound on n. So let's see, let's let little n be in n, and let's have as our goal that u is bigger than that n. I'll probably erase that when I figure out where I need that fraction to go, but that's my goal. How would you want to go between these two things? So I know that u is at least as big as every integer. So if I knew that n were an integer, then I would be done. Is that n an integer? Yeah. Are the integers a subset of z? Yeah, there you go. Let n in n. So as n is a subset of z, n is in z. So as U is an upper bound for Z, oh, the spacing actually worked out well. U is bigger than or equal to n. Oh, neat. So U is in fact an upper bound on n. Why is that a contradiction? What did we just prove moments ago?
Oh,
Yeah.
that is unbounded.
Yeah, so we found an upper bound on a set that's unbounded. There's a contradiction. By theorem 2.5.2, also known as Archimedes Property, n is not bounded above. This is a contradiction. How does that seem? Does that seem pretty okay? Well, it says it's neither bounded above nor is it bounded below, so we're like halfway there. We have that it's not bounded above. Let's try to come up with a proof that it's not bounded below. Let's try to come up with a proof that it's not bounded below. And maybe we'll even try to sketch it. So, let's see. Here are supposed to be like the integers. I don't know, maybe that one's 0. So let's suppose we had a lower bound. So if you had some lower bound L that was less than every integer, how would you what would you want to do if you wanted to turn that thing into an upper bound on Z? Yeah.
Sorry, I was in writing mode. Could you repeat that?
Yeah. So suppose you had a lower bound on the integers. How could you come up with an upper bound on the natural numbers? So, you know that L has to be less than -1, and less than -2, and less than -3, less than -4. So you have a bunch of inequalities that look like that. How could you get something bigger than every natural number? What happens when you, multiply by -1, right? L is less than 4, so negative L must be bigger than 4. Yeah, so I think there's the procedure. Now let's actually just put that into words. Thus Z is not bounded below. Let's suppose that Z is bounded. Z is not bounded above. Below. Let's suppose that Z is bounded below. Let L be a lower bound on Z. That's what you get when you assume something's bounded below. It has a lower bound. We could even assume it had an infimum, I guess. But I think this is an easier thing to do. Let L be a lower bound on Z. So it looks like we think that negative L is an upper bound on N. So let's try to show that. Let's see, for any natural number N, is negative N an integer if N is a natural number?
Yes.
Yeah. So negative N is in Z. Since L is a lower bound on Z, what can you conclude? So between this fact and that fact, what can you conclude? Yeah.
Negative N is an upper bound on Z?
No.
Or N?
No.
Wait.
You can conclude an inequality. L is a lower bound on a set. Here's a thing in the set. So that's probably what you meant when you said the word bound. Right? It gives you a bound on L. All right, and you told me to multiply both sides by -1, so let's multiply both sides by -1. Negative L is then bigger than or equal to N. Oh, hey, have we just demonstrated a single number that is at least as big as every natural number? Yeah, there's a contradiction. Thus, negative L is an upper bound on n, contradicting Archimedes Property version 1. Nice. We feel pretty good? Any questions about how the proof of that corollary went? Cool. All right, Archimedes property version 2. Let's suppose a and b are real numbers, and 0 is less than a. Then there exists a natural number n such that a times n is greater than b. I think I'm going to give two proofs of this because when I wrote this, I was feeling very contradiction-y. So let's come up with a proof by contradiction. And then we'll give a direct proof off to the side. Cool. So we need to show that for every two real numbers with a bigger than 0, that there exists a natural number n such that this happens. So we want to show for every a and b in the real numbers, if a is bigger than 0, then there exists a natural number n such that a times n is bigger than b. There's what we need to show. So if we're going to proceed by contradiction, let's negate that, and that's the thing that we get to assume for the sake of contradiction. So this is a universally quantified thing. So it must be that there exists a counterexample. So there must exist an a and a b in the real numbers, such that the negation of that if-then holds. Well, how can an if-then statement be false? Yeah.
The opposite is true.
What do you mean by opposite?
If you have like a binary case of true or false, if you have the other option be the correct answer.
If today is Tuesday, then it is raining. Is that a true statement? If not, why not? Yeah.
Are we looking for like a contrapositive?
Nope, I just want you to negate an if then. So that statement is false because there exists at least one Tuesday when it didn't rain. So an if then is false means that the assumption is true and the conclusion is false. So we need to construct an A and B and R such that A is bigger than 0 and this is false. And let's see. This is there exists a natural number which satisfies some conditions. Negate that means every natural number fails to satisfy those conditions. So there exists an A and B in the real numbers such that A is bigger than 0, and for every natural number n, A times n is less than or equal to b. And now I'm getting below where you can see, but I'm done writing now. So there's what we get to assume. Assume for contradiction. So let's try to do that. So let's let A and B be real numbers. Assume that A is bigger than 0. A and B are real numbers. Assume that A is bigger than 0. Okay, so I guess I'm jumping straight to negating the if then. For the sake of contradiction, we will assume that for every natural number n, A times n is less than or equal to b. All right, so let's muck around with this. A times n is less than or equal to b, and that is true for absolutely every natural number. is that? So we know that the natural numbers don't have an upper bound. If you knew that this inequality, or that inequality were true for every natural number n, how would you want to get an upper bound on the set of natural numbers? Well, like b divided by a would do, right? It sure looks like b over a is now bigger than every natural number, which is a contradiction. Okay, cool. So we have our path to a contradiction. Let's just write it down. So multiplying the inequality by a inverse, or dividing by a, we see that for every natural number n is less than or equal to b times a inverse. Oh, wait. So what's an upper bound on the set of natural numbers? Yeah. Yeah. Oh, but that means the natural numbers are bounded above. We know they're not bounded above, so we're done. There's our contradiction. How do people feel about that argument? Cool. Next, let's prove that the infimum of the set of reciprocals, yeah.
When we introduce the inverse of a, we have to prove that that can be thrown in there, or is that fine?
Okay, so now that we've completed the section in which we talked about the form of field axioms, let's just kind of think back. So at some point, did we prove that if A is positive, then A inverse is positive? Yeah, I didn't, but you guys did. I think it was a homework. One of the things that we proved about inequality is you can multiply an inequality by a positive number that resolves the inequality. But we're using those two things. But sometimes those two things are sufficiently fundamental that I know won't cite anything for them. Now that we have the properties that follow from the field axioms, well, black box all of them, because it's basic algebra. You can't do that on the homework in which you prove things, but at this point, from now on, we will. Nice. But yeah, that's something that you should worry about. Like, did we actually prove things about inequalities that they behave correctly? I think we did, but you should worry about that. Nice. All right. The set of reciprocals of the infimum of the set of reciprocals of all of the natural numbers is 0. So we need to show 0 is the infimum. So we need to show two things. We need to show 0 is a lower bound on the set of reciprocals of natural numbers. We need to show that if you have any other lower bound, that lower bound is at least as small as 0. So there are two things we need to prove. Let's prove those two things. Let's prove that 0 is a lower bound. And I think I'm going to follow this model of we want to show 0 is a lower bound. Let's figure out what we need to show. There's space to the side. So if you want to show, we want to show 0 is a lower bound on this set. So if you want to show something is a lower bound, what do you need to show? Yeah.
That all values in the set are greater than that.
Yeah. For every thing in that set, that thing is bigger than or equal to 0? Yeah. Okay, so let's proceed. So let's consider any x in the set of all things that look like 1 over n such that n is in n. Oh, nice. That must mean that x is equal to 1 over n plus some n and n. Cool. So we have our anything, so it looks like then we want to show 1 over n is bigger than or equal to 0. Why is 1 over n bigger than or equal to 0? Yeah.
Because that is the inverse of n, and we know that the inverse of n is positive.
Yeah. Right. N is bigger than 0. That means that 1 over n is bigger than 0. Oh, cool. So let's write that down. as little n is in the set big N, little n is bigger than 0. In fact, it's bigger than or equal to 1. But we don't care about 1 right now. We just care about 0. So n inverse is bigger than 0. Thus, x is bigger than 0, and 0 is a lower bound on this set. Groovy. Feel pretty good? So 0 is a lower bound. How do you show that 0 is the greatest lower bound? Yeah.
You show that x would be greater than all other lower bounds?
Yes. Well, 0 would be greater than or equal to every other lower bound. So we need to consider any lower bound. Show that that lower bound is less than or equal to 0. All right. And those are the things that I suggest will be useful. So we'll proceed by contradiction. So that's already there. Let L be a lower bound on the set of reciprocals of natural numbers. We need to show that L is less than or equal to 0. Let's assume, for contradiction, that L is bigger than 0. So what do I have right now? I have L is bigger than 0, and maybe I'll write this down also, as L is a lower bound on N. L is less than or equal to 1. Nope, not on N. Let's give the set a name. I'm going to call this set X. So I can stop writing that set builder notation. So let's call the set big X. L is a lower bound on X, so L is less than or equal to 1 over N for all N in N. Nice. All right, so we want to get a contradiction. Now we've written down, I think, all of this maximally simplified. We have a number L, which is bigger than 0. We know that L is bigger than 0, and L is less than 1 over N for every natural number N. Let's do some stuff. What can that be turned into? Focus on the L is less than or equal to 1 over N. What would you want to do to that? Yeah.
Could we make it negative?
We could make it negative. Maybe I'll suggest instead of making it negative, doing something with those reciprocals. Yeah. Yeah, all right, so maybe I'll do this in 2 steps. N is a natural number, so I can multiply both sides of an inequality by N. As little n is bigger than 0, what do we see? We see N times L is less than or equal to 1. As L is bigger than 0, 1 over L is bigger than 0. So N, multiply both sides of this by 1 over L. N is less than or equal to 1 times 1 over L. Oh, neato, yeah.
Is the n times L less than or equal to 1 just based on the natural numbers estimate?
So let's write that down. As n is bigger than 0, we can multiply both sides of L less than or equal to 1 over n by n.
Oh, sorry. Never mind.
Yeah. But the fact that it's unclear means it needs to be written down. L times n is less than or equal to 1. Similarly, multiply by 1 over L, which is bigger than 0, we get n less than or equal to 1 over L. Nice. And we said we wanted to get a contradiction. What contradiction did we get? So we now know that for absolutely every natural number n is less than 1 over L. As I said, a natural number bounded above? No. But what have we just constructed? Yeah.
So the upper bound would be 1 over L.
Yeah, so it looks like 1 over L is an upper bound on the set of natural numbers. 1 over L is an upper bound on n. This is a contradiction. So, it must be that L is less than or equal to 0. And now, I guess, just a closing statement. So what have we proven? We've proven that 0 is a lower bound on x, and for every lower bound L of x, L is less than or equal to 0. Are those the two things you need to show if you want to show a thing is the infimum? Yeah, it's a lower bound and it's greater than or equal to every other lower bound. Thus, 0 equals the infimum of, and now I guess I'll put this back. Groovy. All right. 15 minutes to go. I think we're set. So the only thing I have left in terms of things called the Archimedes property is that Q is dense in the reals. Between any two distinct reals, there is a rational number. In order to do that, I'll give some structure. So the first thing I want is for any real number, there's an integer somewhere between z and z plus 1. I'll need that first, and then I'll move from there. Any questions first? Okay. Ooh. Flip page. All right. So, I guess one thing is missing. Consider any z in the real numbers. We need to find a natural number n satisfying this inequality. So here's an outline. Here's what we'll do. First, we'll think about all of the natural numbers this is wrong. This is so. Right. For any z in R, there's an integer, not a natural number, an integer in that set. So, we need to find an integer, n in z, satisfying this inequality. All right, so here's the plan that we'll take. First, we'll consider the set of all natural numbers. Yeah. Yes. So we'll consider the set of all not natural numbers but integers. Which satisfy one of the two inequalities. we'll show it's non-empty and bounded above. I guess the bounded above is obvious. Z is an upper bound on the set of all things that are less than Z. Or Z plus 1 is. What do I know about sets that are non-empty and bounded above? They have a supremum? Oh. So we'll let S be the supremum of that set. We'll find an element of the set that lies between S minus 1 and S. That element will be the thing that we will need. So, are we happy that this is a strategy anyway? All right, let's do it. So, let's let A be the set of all natural numbers. Well, okay, so let's actually draw the picture. So, there's this number Z plus 1. It's an upper bound on the set, so the supremum S is somewhere less than it. There's something in the set between S and S minus 1. And something in N. And that's the thing that we'll use. Right, so it's a big A be the set of all integers which are less than Z plus 1. Explain why A is not empty. Well, for starters, is Z plus 1 a lower bound on the set of integers? No, why not? Yeah.
Didn't you just say Z plus 1 was an upper bound?
Yeah, but, well, that was in the sketch, and it was on this set A. Focus on this sentence. Why is Z plus 1 not a lower bound on the set of integers? And I saw other heads shaking. So why can that not be true? Do the integers have any lower bounds? Yeah, that's it. There are no lower bounds, so Z isn't a lower bound. That's it. Z has no lower bounds. And that is corollary 2.5.4. So Z plus 1 is not a lower bound on the integers. Nice. So what does it mean to not be a lower bound? It means there's something in the set lower than it. So there exists some n in Z with n less than Z plus 1. And look at that bit in purple. Is that element that we just conjured into existence an element of the set big A? Is it an integer? Is it less than or equal to Z plus 1? Yeah.
Would you be able to zoom in?
Oh, yeah, sorry. So this natural number n is this integer n is an integer, and we just checked that it's less than Z plus 1. So this n is in the set big A, and A is not equal to the empty set. How do you show something's non-empty? You show something's in it. You just explain why Z plus 1 is an upper bound on the set big A. Let's see. For any n in the set big A, it must be that n is an integer, and n is less than or equal to Z plus 1. Oh wait, did we just accidentally get what we needed just by writing down the definition? Yeah. So, Z plus 1 is an upper bound. Do we feel pretty okay so far? Nice. All right, so this set A is non-empty, bounded above. It has a supremum. We'll let the supremum be S. Since S minus 1 is not less than S minus 1 cannot be an upper bound. So there must be something in the set A so that S minus 1 is less than this element of this set, big A. We feel okay right now? So, right, there are two levels of understanding that you might have in a proof. One is, why is this a good thing to do? And there's been no attempt made to explain that. The hope is we'll see that it's a good thing to do by proving the theorem. So it might not be until we conclude, thus, there exists an integer between z and z plus 1. It might take us that long to get the desired result. But sometimes that's just the way it is. So let's continue waiting through and see what we can do. All right, so there's an element of A which is bigger than S minus 1. This number n is in the set big A, so we conclude that this n is less than or equal to z plus 1. Are we happy? Are we feeling pretty okay right now? All right. On the other hand, since s minus 1 is less than n, it follows that s is less than n plus 1. But wait, s is an upper bound. So is it possible that n plus 1 could possibly be an A? No, it's bigger than an upper bound. That's something that's nice about upper bounds. Cool, so this thing can't be an A, so it cannot satisfy this definition. So it must follow that n plus 1 is not less than or equal to z plus 1, so it must be strictly bigger than z plus 1. We feel okay so far? And now let's just try to gather together the things that we have. Oh, n plus 1 is bigger than z plus 1, so n is bigger than z. All right. So what things do I have right now? I have that n is bigger than z. And I have n is less than or equal to z plus 1. Are those the two things that I actually just needed? Yeah, there we go. So we now see that n is less than z, is less, nope, z is less than n, is less than or equal to z plus 1, which is exactly what we needed to do. Yeah?
Some language is throwing me off here, and I wonder if it's just me or not. So we have, right, so on the other hand, since s is less than n plus 1, and s is an upper bound on a, n plus 1 is not an a.
Yes.
So if we know s is the supremum, right? So then wouldn't it be that because s is the supremum, because if n plus 1 is greater than the supremum, wouldn't it still be an upper bound on a?
Yeah, n plus 1 is also an upper bound on a, but that's not the thing that's important.
Okay.
So, this thing is bigger than the supremum of the set.
Yep.
The supremum is an upper bound. So nothing in the set can be bigger than s.
Yes.
So if this thing is bigger than s, it cannot possibly be in the set.
But is that because s is a supremum or just because s is an upper bound?
Oh, just because s is an upper bound.
Oh.
Yeah, so that's why I said s is an upper bound.
Okay.
So you could put the one is the supremum, and it would also be correct.
Okay.
Cool. So let's think about like the strategy that this proof follows. So this proof that the statement was, for any real number z, you can find an integer between a real number and a real number plus 1. So I said, well, let's consider the set of all natural numbers, all integers, which satisfy one of those two inequalities. So just consider the set of all of them, every element of that set that satisfies one of the two inequalities. Let's try to grab the biggest element of the set and hopefully that satisfies the other inequality. But there's no such thing as the biggest element of the set. You need the between them. And so that's what we did. And from there we'll solve what we know. Maybe making some manipulation. So the last thing in the list is the density of the rational numbers. And I don't have enough time to complete the proof. Well, maybe I do. Let's at least sketch the proof. So, here's the game. Here's how we'll play it. So, you have two rational numbers, x less than 1. So let's suppose that I knew the difference between them was bigger than 1. So let's suppose I knew that like x plus 1 lived there. Then can I take advantage of the thing that we just proved? Don't look at the proof of what we just proved. Just look at the statement. Yeah, I would know that there is a natural number n in there. Every natural number is a rational number, so we know. All right, but what if like x times y is really, really little? What if like y is like x plus 1 over 10,000? Can I multiply x and y by something big enough to get y minus x to be bigger than 1? Yeah, that's one of the things we proved, right? So x times something to y times something. That gap is bigger than 1. Can I find an integer in here? Yeah, so then I will get x n is less than n is less than y n. Can I divide both sides by big N? Will that give me what I need? All right, so that was very fast. But hopefully people feel like they believe that there is a path to a proof using the ingredients we have. So we'll wrap that up next time. I'll hit stop recording, and then before people leave,